In the quiet landscapes of early 19th century Scotland, where rolling green hills met endless gray skies, a child was born who would one day unlock the invisible harmony of the universe. James Clerk Maxwell entered the world on June 13, 1831, in Edinburgh, a time when science was still in its infancy, when mysteries about electricity, magnetism, and light hovered on the edge of imagination. Few could have guessed that this fragile child, born into a modest yet cultured Scottish family, would grow into the mind that united those invisible forces and changed humanity's understanding of the cosmos. His early life was not marked by privilege or luxury, but by curiosity, an unquenchable fire that seemed to burn within him from the moment he could think and see. Maxwell's father, John Clerk Maxwell, was a man of intellect and discipline, a lawyer by training but an engineer at heart. He inherited the family estate of Glenlair in the rolling countryside of Galloway, where young James spent most of his childhood. His mother, Frances Kay, was a woman of exceptional warmth and intelligence, whose gentle voice and encouragement shaped the first sparks of James's curiosity. She nurtured in him the habit of questioning, of seeking patterns in the everyday world. When most children his age were absorbed in games, James was fascinated by how things worked, the way light danced across water, how colors mixed on a surface, or how a spinning top could balance so perfectly. Frances often told friends that her son seemed to live inside a world of wonder, constantly exploring ideas far beyond his years, but childhood wonder often grows alongside isolation. Life at Glenlair was quiet and remote, far from the bustling centers of learning and culture. The estate's vast fields, the gentle hum of wind across stone walls, and the reflective silence of Scottish moors became his first teachers. Here, surrounded by nature, Maxwell began observing the world not just as scenery, but as a living system governed by laws waiting to be uncovered. He would spend hours drawing intricate patterns in the sand, tracing shapes with strings, or studying how light scattered through a glass of water. Even then, a seed of scientific thought was forming, the belief that beauty and order are woven deep into the fabric of the universe. When Maxwell was 8, tragedy struck. His mother, who had been his closest companion and intellectual guide, fell ill with abdominal cancer and passed away. Her death left a void that could not easily be filled. His father, heartbroken but devoted, took charge of the boy's education, determined to keep alive the spark his wife had ignited. John Clerk Maxwell encouraged young James to explore freely, to build, to question, and to record his observations. This father-son partnership became the cornerstone of Maxwell's development, a blend of guidance and freedom that allowed his mind to wander into the vast unknown. His father's open-minded engineering spirit merged with his mother's thoughtful curiosity, shaping a balance between imagination and discipline that would later define his scientific genius. At the age of 10, Maxwell's talents began to reveal themselves in remarkable ways. He had developed an unusual fascination with geometry, drawn not from textbooks, but from the patterns he found in everyday life. Using bits of string, he would stretch shapes across wooden frames to study how lines and circles connected. His fascination grew into an obsession. He would speak of lines of force and curves of beauty. Long before he had formal training in mathematics, his family noticed that James did not just see the world, he analyzed it. The arrangement of petals in a flower, the reflection of light on a pond, even the motion of spinning wheels all seemed to whisper hidden rules to him. Though he didn't yet know it, those hidden rules would one day become the language of field theory, the invisible framework that explains how energy moves through space. When he turned 11, Maxwell's father decided to send him to Edinburgh Academy, a significant step for a boy from the countryside. There, his quiet and awkward nature made him an easy target for teasing, yet his mind quickly drew the attention of teachers and classmates. He was different, not just in ability, but in how he thought. While others memorized lessons, Maxwell wanted to see the logic behind them. He often carried notebooks filled with drawings of ovals, curves, and symmetrical designs, as if trying to decode nature's geometry. His schoolmates nicknamed him Dafty, meaning odd or eccentric, but that label masked the brilliance that was already taking shape within him. Maxwell's intelligence was not loud, it was quiet, profound, and limitless. Under the guidance of his mathematics teacher, James Forbes, and his friend Lewis Campbell, Maxwell's potential began to flourish. His teachers quickly recognized that the boy's mind worked on a different plane. At just 14, he presented his first scientific paper to the Royal Society of Edinburgh, a remarkable feat for someone barely in his teens. The paper, titled On the Description of Oval Curves, explored methods of constructing geometrical shapes using string and pins. Though he was too young to present it himself, his work astonished the Society's members. This was not merely the curiosity of a child, it was the early emergence of a methodical, creative mind destined to change science. That paper foreshadowed his later discoveries about electromagnetic fields, showing how invisible connections could define visible forms. Despite his growing academic reputation, Maxwell remained humble and deeply introspective. He often returned to Glenlair, retreating into solitude to think and observe. He loved poetry, philosophy, and theology as much as mathematics. To him, science was not just calculation. It was a way of discovering beauty and truth. He saw no divide between art and mathematics, between wonder and logic. The patterns that others saw as mere coincidence, he regarded as the signatures of a deeper order. That unity between science and spirit would guide his philosophy throughout life. When Maxwell entered the University of Edinburgh at the age of 16, he was already far ahead of his peers. There he immersed himself in physics, optics, and mechanics, often conducting experiments at home. He was known to spend late nights polishing lenses, experimenting with prisms, and exploring the nature of light. The flicker of a candle, the shimmer of colors through glass, or the reflection on a metallic surface, all became sources of inquiry. Light fascinated him because it seemed to hold both mystery and law, both chaos and order. It was not just brightness to Maxwell, it was a message from the universe waiting to be decoded. His early professors soon realized that Maxwell possessed not only a great mind, but a rare kind of creativity, a capacity to connect ideas from entirely different realms. He might study the play of light on soap bubbles and use it to theorize about electromagnetic waves. He could look at a rotating disk and imagine how motion and color interacted. Even as a student, he began to challenge the scientific boundaries of his day, blending observation with mathematical abstraction. While most scientists sought answers through experiments alone, Maxwell sought harmony, an understanding of why nature behaved as it did. Yet, behind his growing brilliance lay a deeply human side. Maxwell was shy, sometimes socially awkward, and often lost in thought. He preferred quiet walks through the countryside or evenings spent reading to crowded gatherings. Those who knew him described him as gentle, humorous, and deeply kind, a man with a sharp intellect but a humble heart. He believed knowledge should serve truth, not pride. In a letter to a friend, he once wrote that, "The aim of science is not to master nature, but to understand her ways." It was this humility, this sense of awe, that gave his genius a timeless quality. In these early years, Maxwell's life was a delicate balance between solitude and discovery, between personal loss and intellectual triumph. The death of his mother had left a shadow, but it also gave him an inner strength, a determination to seek meaning beyond pain. His faith, his love for nature, and his father's encouragement became the pillars upon which his mind flourished. Every observation he made, every sketch he drew, carried a silent dedication to the mother who had once told him to look deeper, for there is always more to see. By the time Maxwell completed his studies in Edinburgh, he had already formed the foundations of what would later become his life's philosophy, that the universe is not a random chaos but a symphony of relationships. Every color, every vibration, every wave was part of a greater harmony, a concept he would later express mathematically in the language of electromagnetic theory. He had not yet discovered his famous equations, But the mental groundwork was laid. The curiosity that began in childhood, with strings stretched across wooden frames, had evolved into a powerful vision of unity in nature. His journey from the hills of Galloway to the intellectual halls of Edinburgh was more than academic. It was spiritual. It was the awakening of a mind that would one day connect electricity and magnetism, light and energy, the seen and the unseen. The young boy who once traced patterns in the sand had learned to trace the patterns of the cosmos itself. The same curiosity that made him stare at colors through glass now drove him toward the frontiers of physics, where few dared to imagine that invisible forces could be united by mathematics. This was only the beginning of Maxwell's story, the genesis of a genius who would redefine the laws of nature. His early life was not a tale of privilege or fame but of pure, unbridled curiosity. Every question he asked as a child became a stepping stone toward his destiny to show the world that the universe is a single, elegant web of forces, connected, harmonious, and profoundly beautiful. In the quiet landscapes of early 19th century Scotland, where rolling green hills met endless gray skies, a child was born who would one day unlock the invisible harmony of the universe. James Clerk Maxwell entered the world on June 13, 1831, in Edinburgh, a time when science was still in its infancy, when mysteries about electricity, magnetism, and light hovered on the edge of imagination. Few could have guessed that this fragile child, born into a modest yet cultured Scottish family, would grow into the mind that united those invisible forces and changed humanity's understanding of the cosmos. His early life was not marked by privilege or luxury, but by curiosity, an unquenchable fire that seemed to burn within him from the moment he could think and see. Maxwell's father, John Clerk Maxwell, was a man of intellect and discipline, a lawyer by training but an engineer at heart. He inherited the family estate of Glenlair in the rolling countryside of Galloway, where young James spent most of his childhood. His mother, Frances Kay, was a woman of exceptional warmth and intelligence whose gentle voice and encouragement shaped the first sparks of James's curiosity. She nurtured in him the habit of questioning, of seeking patterns in the everyday world. When most children his age were absorbed in games, James was fascinated by how things worked, the way light danced across water, how colors mixed on a surface, or how a spinning top could balance so perfectly. Frances often told friends that her son seemed to live inside a world of wonder, constantly exploring ideas far beyond his years. But childhood wonder often grows alongside isolation. Life at Glenlair was quiet and remote, far from the bustling centers of learning and culture. The estate's vast fields, the gentle hum of wind across stone walls, and the reflective silence of Scottish moors became his first teachers. Here, surrounded by nature, Maxwell began observing the world not just as scenery, but as a living system governed by laws waiting to be uncovered. He would spend hours drawing intricate patterns in the sand, tracing shapes with strings, or studying how light scattered through a glass of water. Even then, a seed of scientific thought was forming, the belief that beauty and order are woven deep into the fabric of the universe. When Maxwell was 8, tragedy struck. His mother, who had been his closest companion and intellectual guide, fell ill with abdominal cancer and passed away. Her death left a void that could not easily be filled. His father, heartbroken but devoted, took charge of the boy's education, determined to keep alive the spark his wife had ignited. John Clerk Maxwell encouraged young James to explore freely, to build, to question, and to record his observations. This father-son partnership became the cornerstone of Maxwell's development, a blend of guidance and freedom that allowed his mind to wander into the vast unknown. His father's open-minded engineering spirit merged with his mother's thoughtful curiosity, shaping a balance between imagination and discipline that would later define his scientific genius. At the age of 10, Maxwell's talents began to reveal themselves in remarkable ways. He had developed an unusual fascination with geometry, drawn not from textbooks but from the patterns he found in everyday life. Using bits of string, he would stretch shapes across wooden frames to study how lines and circles connected. His fascination grew into an obsession. He would speak of lines of force and curves of beauty long before he had formal training in mathematics. His family noticed that James did not just see the world, he analyzed it. The arrangement of petals in a flower, the reflection of light on a pond, even the motion of spinning wheels all seemed to whisper hidden rules to him. Though he didn't yet know it, those hidden rules would one day become the language of field theory, the invisible framework that explains how energy moves through space. When he turned 11, Maxwell's father decided to send him to Edinburgh Academy, a significant step for a boy from the countryside. There, his quiet and awkward nature made him an easy target for teasing, yet his mind quickly drew the attention of teachers and classmates. He was different, not just in ability, but in how he thought. While others memorized lessons, Maxwell wanted to see the logic behind them. He often carried notebooks filled with drawings of ovals, curves, and symmetrical designs, as if trying to decode nature's geometry. His schoolmates nicknamed him Dafty, meaning odd or eccentric, but that label masked the brilliance that was already taking shape within him. Maxwell's intelligence was not loud, it was quiet, profound, and limitless. Under the guidance of his mathematics teacher, James Forbes, and his friend Lewis Campbell, Maxwell's potential began to flourish. His teachers quickly recognized that the boy's mind worked on a different plane. At just 14, he presented his first scientific paper to the Royal Society of Edinburgh, a remarkable feat for someone barely in his teens. The paper, titled On the Description of Oval Curves, explored methods of constructing geometrical shapes using string and pins. Though he was too young to present it himself, his work astonished the Society's members. This was not merely the curiosity of a child, it was the early emergence of a methodical, creative mind destined to change science. That paper foreshadowed his later discoveries about electromagnetic fields, showing how invisible connections could define visible forms. Despite his growing academic reputation, Maxwell remained humble and deeply introspective. He often returned to Glenlair, retreating into solitude to think and observe. He loved poetry, philosophy, and theology as much as mathematics. To him, science was not just calculation, it was a way of discovering beauty and truth. He saw no divide between art and mathematics, between wonder and logic. The patterns that others saw as mere coincidence, he regarded as the signatures of a deeper order. That unity between science and spirit would guide his philosophy throughout life. When Maxwell entered the University of Edinburgh at the age of 16, he was already far ahead of his peers. There he immersed himself in physics, optics, and mechanics, often conducting experiments at home. He was known to spend late nights polishing lenses, experimenting with prisms, and exploring the nature of light. The flicker of a candle, the shimmer of colors through glass, or the reflection on a metallic surface, all became sources of inquiry. Light fascinated him because it seemed to hold both mystery and law, both chaos and order. It was not just brightness to Maxwell, it was a message from the universe waiting to be decoded. His early professors soon realized that Maxwell possessed not only a great mind, but a rare kind of creativity, a capacity to connect ideas from entirely different realms. He might study the play of light on soap bubbles and use it to theorize about electromagnetic waves. He could look at a rotating disk and imagine how motion and color interacted. Even as a student, he began to challenge the scientific boundaries of his day, blending observation with mathematical abstraction. While most scientists sought answers through experiments alone, Maxwell sought harmony, an understanding of why nature behaved as it did. Yet, behind his growing brilliance lay a deeply human side. Maxwell was shy, sometimes socially awkward, and often lost in thought. He preferred quiet walks through the countryside or evenings spent reading to crowded gatherings. Those who knew him described him as gentle, humorous, and deeply kind, a man with a sharp intellect but a humble heart. He believed knowledge should serve truth, not pride. In a letter to a friend, he once wrote that, "The aim of science is not to master nature, but to understand her ways." It was this humility, this sense of awe, that gave his genius a timeless quality. In these early years, Maxwell's life was a delicate balance between solitude and discovery, between personal loss and intellectual triumph. The death of his mother had left a shadow, but it also gave him an inner strength, a determination to seek meaning beyond pain. His faith, his love for nature, and his father's encouragement became the pillars upon which his mind flourished. Every observation he made, every sketch he drew, carried a silent dedication to the mother who had once told him to look deeper, for there is always more to see. By the time Maxwell completed his studies in Edinburgh, he had already formed the foundations of what would later become his life's philosophy, that the universe is not a random chaos but a symphony of relationships. Every color, every vibration, every wave was part of a greater harmony, a concept he would later express mathematically in the language of electromagnetic theory. He had not yet discovered his famous equations, but the mental groundwork was laid. The curiosity that began in childhood, with strings stretched across wooden frames, had evolved into a powerful vision of unity in nature. His journey from the hills of Galloway to the intellectual halls of Edinburgh was more than academic. It was spiritual. It was the awakening of a mind that would one day connect electricity and magnetism, light and energy, the seen and the unseen. The young boy, who once traced patterns in the sand, had learned to trace the patterns of the cosmos itself. The same curiosity that made him stare at colors through glass now drove him toward the frontiers of physics, where few dared to imagine that invisible forces could be united by mathematics. This was only the beginning of Maxwell's story, the genesis of a genius who would redefine the laws of nature. His early life was not a tale of privilege or fame but of pure, unbridled curiosity. Every question he asked as a child became a stepping stone toward his destiny, to show the world that the universe is a single, elegant web of forces, connected, harmonious, and profoundly beautiful. In the heart of the 19th century, when the world was still grasping the mysterious behavior of electricity and magnetism, a quiet Scottish physicist began a journey that would forever reshape humanity's understanding of the invisible forces governing reality. James Clerk Maxwell, already known for his genius in mathematics and color theory, turned his attention toward a question that had haunted scientists for generations: what truly connects electricity, magnetism, and light? The answer he would uncover was nothing short of revolutionary, a discovery that would illuminate not just laboratories, but the entire universe. To appreciate the depth of Maxwell's groundbreaking work, one must first understand the world he inherited. When he began his studies, science was a patchwork of isolated discoveries. In London, Michael Faraday had demonstrated that electricity could produce magnetism and vice versa, through his pioneering experiments with coils and magnets. His concept of lines of force, invisible threads through which magnetic and electric influences moved, was powerful but lacked mathematical form. Faraday could see the fields intuitively, but he could not describe them in equations. On the other hand, scientists such as André, Marie Ampère and Carl Friedrich Gauss had developed equations that explained pieces of the puzzle, but their work remained fragmented. The scientific world stood divided between intuition and mathematics, vision and precision. It was Maxwell who bridged that divide. His mind, trained both in geometry and logic, had a rare gift for seeing unity in diversity. He could take Faraday's visual imagination and translate it into the exact language of mathematics. To Maxwell, the invisible fields that Faraday described were not just metaphors. They were physical realities, continuous fabrics stretching through space. He believed that these fields carried energy, tension, and motion, much like waves in water or vibrations in air. But to prove that idea, he needed a new kind of physics, one that could express invisible motion in visible equations. Between 1855 and 1865, Maxwell immersed himself in this challenge with relentless curiosity. He began constructing models, both physical and mental, to represent how electric and magnetic fields interacted. In one famous analogy, he imagined space filled with tiny rotating vortices connected by elastic tubes that transmitted force. It was an imaginative attempt to explain how a change in one part of an electromagnetic field could affect another. Though the model itself was only a stepping stone, it helped Maxwell visualize the concept of energy moving through space, a concept no one before him had clearly defined. What emerged from these efforts was the realization that electricity and magnetism were not separate phenomena, but two sides of the same fundamental process. In 1861, Maxwell published his first major paper on the subject, On Physical Lines of Force. In this groundbreaking work, he expressed Faraday's ideas mathematically for the first time. He proposed that electromagnetic phenomena could be understood as interactions within a continuous medium, which he called the electromagnetic field. To Maxwell, this field was not merely a convenient abstraction. It was a real entity that carried energy, stored stress, and propagated motion. In his equations, he began to describe how a changing electric field could create a magnetic field, and how a changing magnetic field could, in turn, produce an electric one. This self-sustaining interaction suggested something profound, that these fields could travel through space, forming waves. As Maxwell explored this idea further, he made a discovery that would forever transform physics. When he calculated the speed at which these electromagnetic disturbances would move through space, he found that the number was astonishingly close to the known speed of light. The realization struck him like a revelation. Light itself must be an electromagnetic wave. In that moment, centuries of speculation about the nature of light were unified under a single principle. What Newton had studied as particles, what Huygens had described as waves, and what Faraday had sensed as vibration in fields, all were facets of the same truth. Maxwell wrote with quiet triumph, "We can scarcely avoid the conclusion that light consists in the transverse undulations of the same medium, which is the cause of electric and magnetic phenomena." This was the birth of electromagnetic theory, the unification of electricity, magnetism, and optics into one coherent framework. The impact of this insight cannot be overstated. For the first time, scientists understood that light was not a mysterious or separate force, but part of the same continuum that powered electric currents and magnetic attraction. It was an elegant and astonishing synthesis. Nature, once thought divided into distinct forces, was revealed to be fundamentally connected. Through four equations, simple in form yet vast in implication, Maxwell had written the language of the universe's invisible architecture. But reaching this understanding was not easy. Maxwell's equations did not emerge in a single burst of inspiration. They evolved through years of struggle, revision, and contemplation. He worked tirelessly to refine his models, testing his mathematics against known laws of electricity and magnetism. Each term in his equations represented a physical idea, an expression of energy, motion, or force. Yet it was one additional term, added almost intuitively, that completed the picture. While studying how electric currents behave in circuits, Maxwell realized that even when no physical charge was moving, such as in a capacitor where electricity is stored, a changing electric field still produced magnetic effects. To account for this, he introduced what he called the displacement current, an invisible flow that allowed the continuity of electromagnetic motion through empty space. This single insight closed the gap in the laws of electricity and magnetism, transforming them into a perfectly self-consistent system. With the displacement current, Maxwell's equations became alive, capable of describing how energy travels not just through wires, but through the vacuum of the universe. It was a leap of imagination that changed science forever. Before Maxwell, the concept of empty space meant void and silence. After Maxwell, it became a sea of fields vibrating with invisible waves. Space itself, he revealed, was not empty but dynamic, filled with energy that connected everything. This was more than a scientific discovery. It was a philosophical revelation, Maxwell had shown that the universe was not a collection of isolated objects, but an interconnected whole, bound by continuous forces that transcended distance. By 1865, Maxwell had consolidated his ideas into his monumental paper, A Dynamical Theory of the Electromagnetic Field. It was one of the most profound works in the history of physics, comparable only to Newton's Principia. In it, he presented the complete set of what would later be known as Maxwell's equations. They were 4 in number, though originally expressed in a much more complex form than the compact vector notation used today. These equations described how electric charges produce electric fields, how moving charges produce magnetic fields, how changing magnetic fields induce electric currents, and how these interactions propagate as waves. Each equation was like a verse in a cosmic poem. Together, they sang of unity, symmetry, and elegance. With them, Maxwell had built a bridge across the invisible. When his paper was first published, few fully understood its depth. The mathematics was dense and the implications almost unbelievable. Some of his contemporaries admired the beauty of his reasoning, but doubted whether electromagnetic waves could truly exist. After all, no one had yet seen or measured them directly. Maxwell himself lacked the experimental tools to confirm his predictions, but he was confident in his logic. The equations, he believed, were too harmonious to be wrong. They expressed a truth deeper than experiment, a truth about the structure of nature itself. Maxwell's work marked a shift in the philosophy of science. Before him, physics had largely been about tangible things, forces acting between objects, particles colliding, wires carrying current. After him, it became about fields, continuous entities filling space, capable of storing and transmitting energy without material carriers. The concept of the field became central to all later physics. It redefined how scientists thought about reality itself. No longer was the universe a stage where particles moved. It was a living web of relationships, a tapestry of interactions stretching across infinity. During this period, Maxwell's curiosity extended beyond pure theory. He was deeply concerned with how energy flowed and transformed in physical systems. His study of the electromagnetic field led him naturally to explore the conservation of energy, a principle that was emerging as one of the great unifying laws of nature. He showed that electromagnetic energy could be quantified and localized, that light carried not just motion, but measurable energy density. In doing so, he introduced the idea that energy can exist independently of matter, carried by waves through space. This was a radical departure from classical thinking, yet it laid the groundwork for the future of physics, where energy would become the central concept of all natural phenomena. Maxwell also recognized the far-reaching implications of his theory for technology and communication. Though he never lived to see it, his equations predicted that it would be possible to generate electromagnetic waves of many different frequencies. Not just visible light, but radio waves, microwaves, and beyond. Each would travel at the same universal speed, carrying information across space without the need for wires. Decades later, scientists such as Heinrich Hertz, Guglielmo Marconi, and Nikola Tesla would turn Maxwell's predictions into reality, giving birth to radio, radar, and wireless communication. Every signal transmitted across the air, every broadcast, every data wave sent through space today is a living echo of Maxwell's vision. But Maxwell's influence went deeper still. His unification of electromagnetism transformed not just technology, but the very foundations of theoretical physics. His equations revealed that the speed of light is constant, a fact that puzzled and inspired a young Albert Einstein decades later. Einstein's theory of relativity was, in many ways, a continuation of Maxwell's legacy. It extended the electromagnetic field into the geometry of space and time. When Einstein looked back on his work, he acknowledged Maxwell as one of the few giants on whose shoulders he stood. Without Maxwell's field theory, relativity and quantum mechanics, the twin pillars of modern physics, might never have been conceived. The elegance of Maxwell's equations lies not only in their accuracy, but in their simplicity. Written in modern form, They are astonishingly concise, just 4 relationships connecting electric and magnetic fields. Yet within them lies everything from the operation of electric motors to the propagation of light across the cosmos. They are, in essence, the DNA of the electromagnetic universe. When Maxwell wrote them, he may not have known that he was opening the door to the electronic age. But he certainly knew he had glimpsed something eternal. What made Maxwell's work truly groundbreaking was not merely the mathematics, but the way he thought about nature. He believed that beauty and truth were inseparable in science. If a theory was elegant, if it unified and simplified, it was likely to be true. His equations were beautiful because they mirrored the harmony he believed existed in the cosmos. To him, the role of the scientist was to uncover that harmony, to see through the chaos of phenomena to the order beneath. In this sense, Maxwell's discovery was not just scientific, it was almost artistic. He transformed physics into a language of symmetry and grace. Even today, when physicists describe new forces or particles, they do so through fields governed by equations descended from Maxwell's. His vision of the electromagnetic field became the model for every subsequent field theory, from the strong and weak nuclear forces to the Higgs field and quantum electrodynamics. Every modern description of the universe, from subatomic particles to galaxies, echoes the patterns first drawn by Maxwell's hand. By the time Maxwell completed his great work, the world was still catching up to his vision. The simplicity of his equations disguised their revolutionary nature, but history would soon prove him right. In 1887, 8 years after his death, Heinrich Hertz experimentally confirmed the existence of electromagnetic waves. Waves that behaved exactly as Maxwell's theory predicted. With that discovery, the invisible became visible, and Maxwell's abstract mathematics became the foundation of a new era. The invisible threads he had imagined now carried voices, light, and data through the air, binding humanity in ways he could scarcely have imagined. The seeds of that revolution were sown in his tireless curiosity, the same curiosity that once drove him to explore the colors of light and the geometry of curves. Maxwell's groundbreaking work on electromagnetism was not the product of mere calculation but of wonder. He saw the universe not as a set of isolated effects, but as an interconnected whole where every vibration, every force, every flash of light was part of a single grand symphony. His genius lay not only in solving problems, but in asking deeper questions, questions that revealed the unity of all things. And so, in the quiet rhythm of his equations, Maxwell captured something profound, the pulse of the universe itself. Every time light crosses space, every time a magnetic field ripples or a current flows, his legacy continues to hum through existence. The invisible forces he united are not just physical, they are poetic reminders that knowledge, imagination, and beauty are woven together at the core of creation. As the 1850s unfolded, the scientific world was alive with questions that seemed to stretch beyond the limits of known physics. Electricity and magnetism were now recognized as kindred forces, but no one truly understood how they acted at a distance. Some imagined invisible fluids, others a mechanical medium that transmitted force like gears in a machine. James Clerk Maxwell entered this scene with the calm curiosity of a man who did not want to conquer nature but to converse with it. Each experiment, each page of calculation, was for him an act of translation, turning nature's silent patterns into the clear language of mathematics. When Maxwell moved to London and later to King's College in 1856, he found himself surrounded by an expanding network of thinkers trying to make sense of electric and magnetic phenomena. Faraday had shown that lines of magnetic force were real, but not even Faraday could describe them mathematically. To most physicists, these fields were a useful metaphor, nothing more. To Maxwell, they were as tangible as the tides or the wind. He began to ask, if forces spread through space, could space itself store energy? Could it vibrate, pulse, or transmit motion like the surface of a pond disturbed by a stone? These questions would not merely lead to new experiments, they would reshape the architecture of modern physics. Maxwell's method was unusual. He did not separate imagination from logic, he used each to refine the other. Sitting at his desk, he would sketch loops and curves that represented the movement of invisible fields. He saw electricity and magnetism not as static phenomena, but as patterns in motion, swirling and interweaving through the ether. The idea of the luminiferous ether was still accepted then, the mysterious substance thought to carry light waves through empty space. But Maxwell's mathematical insight began to suggest that perhaps the ether was not a separate entity at all. Maybe space itself possessed the ability to host vibrations of electric and magnetic energy. His equations, still forming in rough notebooks, hinted at this possibility long before he realized its magnitude. While working at Marischal College in Aberdeen, Maxwell was surrounded by a quiet Scottish landscape that mirrored the calmness of his thought. But beneath that calm ran a deep current of creativity. He conducted experiments on color perception, building a color wheel that could reproduce any hue by spinning red, green, and blue segments, a discovery that would later inform color photography and television. Yet even as he explored optics, his mind kept returning to the same haunting question: what unites the phenomena of electricity, magnetism, and light? In his private notes, he began to see that these three were not distinct kingdoms of science but facets of one continuous reality. By 1861, Maxwell's equations were beginning to take form. He approached the relationship between electric and magnetic fields as a kind of dance, each force giving birth to the other in rhythmic succession. When an electric field changes, it creates a magnetic field. When the magnetic field changes, it regenerates the electric. This self-propagating cycle could, in theory, travel through space as a wave. What kind of wave? Maxwell calculated its speed using the best measurements of the electric and magnetic constants available at the time. The result was astonishing. The number matched exactly the known speed of light. That single coincidence illuminated the cosmos like a revelation. Light itself was an electromagnetic wave, energy rippling through space, the visible expression of the same invisible forces that powered every electric spark. When he shared these findings in 1864 with the Royal Society, many physicists were bewildered. The mathematics was elegant but complex, few could follow its meaning. Even those who grasped the results hesitated to believe that light and electromagnetism were identical. Yet Maxwell's conviction never wavered. He understood that truth in science often begins as disbelief. He quietly refined his theory, giving it physical interpretation and intuitive depth. His four great equations, compact, symmetric, and profound, would later stand beside Newton's laws as pillars of modern science. But in 1864 they were the product of a mind still reaching into the unknown, guided more by insight than by acceptance. The later 1860s saw Maxwell settle into a life of balance between academia and the solitude of Glenlair. There, amid the fields of his childhood, he returned to his beloved estate, tending to experiments and writing his treatise on electricity and magnetism. This monumental work, published in 1873, distilled 2 decades of reflection into a comprehensive theory. Every page radiated the calm certainty of a man who had glimpsed the structure behind nature's veil. The treatise did more than describe experiments, it wove a narrative of unity, showing how static charges, currents, induction, and light all obeyed one set of universal laws. The beauty of the equations lay not only in their accuracy but in their harmony. For Maxwell, mathematics was not an abstract tool, it was the poetry of the universe. Behind this intellectual triumph lay long years of patience and resilience. Maxwell's health was fragile, his body often failed him, though his mind never did. Friends recalled seeing him pale and tired, yet absorbed in his calculations as though the numbers themselves gave him life. He lived simply, without the arrogance that often follows genius. When students visited Glenlair, he treated them as equals, inviting them to observe his experiments and join in conversation. To him, discovery was a communal journey, not a solitary conquest. He once wrote, "In science, the most valuable result is the discovery of a new connection." one that shows unity where others saw division. That statement captured the essence of his legacy. During these years, the broader world was transforming. The Industrial Revolution was in full stride, steam engines powered factories, telegraphs connected continents, and railways bound nations together. Yet behind all this progress lay unanswered mysteries about energy, motion, and light. Maxwell's theory provided the invisible scaffolding for this technological age. His equations predicted the existence of waves beyond visible light, radio, infrared, ultraviolet, though he would not live to see them discovered. A generation later, Heinrich Hertz would confirm their existence experimentally, proving that Maxwell had been right. Those invisible waves would eventually carry the voices of humanity through telecommunication, radio, and the entire digital world. As the 1870s progressed, Maxwell's attention shifted toward refining his concepts of energy and field. He sensed that matter itself might not be fundamental, that the true substance of the universe was the field, an interconnected web of energy permeating all space. This idea would later inspire Einstein, who referred to Maxwell's theory as the most profound and the most fruitful that physics has experienced since Newton. Yet in Maxwell's own time, such thoughts were only beginning to bloom. He lacked the experimental tools to prove them. But his equations hinted at a deeper unity, a world where all forces might one day be seen as different expressions of the same underlying fabric. Maxwell's love for teaching never faded. At Cambridge, where he became the first Cavendish Professor of Experimental Physics, he created a laboratory that encouraged young minds to question freely. He was not a stern authority figure, but a mentor who believed in nurturing imagination as much as precision. Students remembered his gentle laughter, his modesty, and his tendency to speak of complex theories with the same warmth as a poet describing the sky. Under his guidance, experimental physics in Britain found a new life. He laid the foundations for future discoveries in electromagnetism, atomic structure, and radiation. His influence would ripple through generations, through Thomson, Rutherford, Einstein, and beyond. Even as his fame grew, Maxwell remained grounded in his Scottish roots. He corresponded with friends about literature, philosophy, and religion, seeing no conflict between faith and science. To him, the laws of nature were not mechanical accidents but signs of divine order. This belief did not limit his curiosity, it expanded it. He saw God not as a gap in knowledge, but as the ultimate source of the universe's harmony. For Maxwell, understanding the electromagnetic field was another way of glimpsing the mind of the Creator. Such humility made him both a scientist and a philosopher of the natural world. By 1878, illness began to shadow his days once again. The same hereditary cancer that had taken his mother returned, quietly and relentlessly. Yet even as his body weakened, his mind continued to work. He spent hours revising notes, refining concepts, and guiding the Cavendish Laboratory's early progress. When visitors asked about his health, he would smile and change the subject to some new experiment or mathematical curiosity. His last letters were filled not with despair but with wonder at the universe he had spent a lifetime trying to understand. In 1879, at the age of 48, James Clerk Maxwell passed away. The news traveled slowly, but its impact was profound. Scientists across Europe mourned not only a great physicist, but a rare soul whose gentleness matched his intellect. His equations, at that time, were known only to a few, but within decades they would form the backbone of all modern physics. Through them, humanity learned that light, electricity, and magnetism are not separate mysteries but one symphony of energy. Maxwell's vision of unity became the guiding principle for the 20th century's revolutions, from Einstein's relativity to quantum electrodynamics and the rise of wireless communication. Today, when we switch on a light, tune a radio, or connect through a satellite, we are living in the echo of Maxwell's insight. He revealed that the universe is not a collection of isolated forces, but a single, dynamic field, a cosmos humming with invisible waves. His life reminds us that true genius lies not in complexity, but in seeing simplicity behind complexity, unity behind diversity. The equations he left behind, 4 lines of mathematical grace, continue to govern everything from the flicker of a star to the glow of a smartphone screen. The legacy of James Clerk Maxwell endures not just in textbooks but in the spirit of discovery itself. He taught the world that imagination and reason are not rivals but partners. His journey from the quiet hills of Galloway to the grand halls of Cambridge is more than the story of a scientist. It is the story of humanity's awakening to the hidden harmony of existence. Every wave that crosses space, every spark that lights the night, carries a silent tribute to the man who saw the unity behind it all. His equations may have described fields and forces, but his true gift was vision. The vision that the universe, in all its vastness, is one. In the mid-19th century, science stood at a crossroads. The industrial world was powered by engines, gears, and wires, machines that had harnessed steam and electricity. Yet no one truly understood what made those mysterious sparks of energy behave as they did. Lightning flashed across the sky, compasses pointed north, and electric currents hummed through telegraph lines, but to most scientists, these were still separate wonders, governed by rules that seemed independent and unconnected. Into this landscape stepped James Clerk Maxwell, a quiet Scottish physicist whose mind reached further than the limits of his time. He saw not isolation but unity, a hidden rhythm beneath the chaos, a law that could bind light, electricity, and magnetism into a single cosmic symphony. The seeds of that realization were already present in the work of those who came before him, scientists like Michael Faraday, whose vision of invisible lines of force filled Maxwell's imagination. Faraday had shown through experiment that electricity and magnetism influenced one another, yet he lacked the mathematical tools to express those ideas fully. Maxwell revered Faraday, calling him the greatest experimental philosopher of the age. But where Faraday saw lines of force as patterns drawn by nature, Maxwell sought to give them mathematical voice. He believed that behind every curve of force and flicker of energy lay equations. Simple, universal expressions that could describe the movement of invisible fields. When Maxwell began formulating his electromagnetic theory, he did not start with assumptions or dogma, but with curiosity and imagination. He imagined space not as empty nothingness, but as a living medium filled with energy, where electric and magnetic forces interacted like waves upon a sea. In his early models, he even pictured tiny rotating vortices, microscopic whirls in an unseen fluid that transmitted energy from one point to another. These images were not literal, but conceptual tools, a bridge between human intuition and the abstract world of mathematics. As he refined his theory, those imaginary vortices dissolved into pure equations, leaving behind the elegant symmetry that would define modern physics. Between 1855 and 1861, Maxwell began publishing a series of papers that slowly unraveled the hidden structure of electromagnetic phenomena. He introduced the revolutionary idea that a changing electric field could produce a magnetic field, and vice versa. This simple insight would change everything. Until then, physicists believed that electric and magnetic effects were generated only by moving charges or magnets. Maxwell showed that even in empty space, where no charge or magnet existed, a disturbance in one field could create a disturbance in the other. Together, they could sustain themselves, propagating through the void as waves of pure energy. And when he calculated the velocity of these waves, it matched the known speed of light with uncanny precision. That was the moment when the universe revealed its secret. Light itself was an electromagnetic wave. It was a discovery as profound as Newton's law of gravitation. Newton had shown that the same force guiding the fall of an apple governed the motion of planets. Maxwell now showed that the same forces that produced electricity and magnetism were responsible for the light that illuminated the world. He had united two great realms of physics under one theory, a unification that would later inspire Albert Einstein's theory of relativity and the entire structure of modern field theory. In one leap, Maxwell had transformed light from a mystical phenomenon into a measurable, mathematical reality. The elegance of Maxwell's insight lay not just in his conclusion, but in the framework he created. He developed a set of equations, 4 concise mathematical statements, that could describe every electric and magnetic event in the universe. They were not mere symbols on paper, they were the heartbeat of nature. Each equation represented a law of balance and motion, linking how electric charges create fields, how those fields evolve, and how they carry energy through space. These equations revealed that energy is not confined to matter. It exists everywhere, even in what appears to be empty space. This idea, radical for its time, would later reshape cosmology, quantum physics, and the way humanity perceives the fabric of reality itself. Yet Maxwell's achievement was not instantly recognized. His papers were long, complex, and filled with difficult mathematics that few could fully grasp. Even great scientists like Lord Kelvin struggled to see the physical meaning behind the symbols. Some dismissed Maxwell's field theory as abstract speculation, preferring mechanical models that fit the industrial logic of the era. But Maxwell's patience and humility never wavered. He continued refining his theory, guided not by fame but by conviction. He understood that truth often walks alone before it is embraced by the world. In 1864, Maxwell presented his now famous paper, A Dynamical Theory of the Electromagnetic Field, to the Royal Society. In it, he articulated for the first time that light is an electromagnetic disturbance propagating through the field, according to the same laws that govern electricity and magnetism. It was a breathtaking synthesis, but the audience, steeped in older traditions, could not yet comprehend the magnitude of what they had heard. Only a few, like William Thomson's later Lord Kelvin, recognized that physics would never be the same again. But even Kelvin, though admiring, hesitated to accept the full implications. The world was not ready for the vision Maxwell had unveiled. As Maxwell continued his work, he found beauty in simplicity. He wrote that the equations describing electromagnetic waves contained nothing in them beyond the fact that light consists of transverse undulations of the same medium, which is the cause of electric and magnetic phenomena. That single sentence bridged centuries of inquiry, from Galileo's telescope to Faraday's wires. It meant that every ray of sunlight, every reflection on a pond, every color seen through a prism, was an electromagnetic vibration echoing through the vastness of space. What humans perceived as light was only a small portion of a much broader spectrum, invisible to the eye but real nonetheless. Maxwell's equations predicted these unseen waves, radio, microwaves, infrared, ultraviolet, X-rays, long before technology could detect them. His theory extended the boundaries of human perception itself. Maxwell's work also introduced a new understanding of energy. Before him, scientists viewed energy as a property confined to matter, something stored in moving objects or chemical reactions. Maxwell revealed that energy could exist independently, carried by fields even in the absence of matter. The electromagnetic field was not just a mathematical tool, but a real physical entity capable of transmitting energy and momentum. This concept was revolutionary, for it suggested that the universe was not a void filled with scattered particles, but a continuous fabric of energy in perpetual motion. Every electric spark, every radio signal, every beam of light was a manifestation of that energy moving through the field. The philosophical implications were equally profound. For Maxwell, this discovery confirmed his lifelong belief that nature's laws were unified and harmonious. He once said, "It is by the harmony of mathematical laws that the Creator has arranged the universe." His work was not merely scientific, but deeply reflective, connecting the physical with the metaphysical. To him, discovering the electromagnetic field was not uncovering chaos but unveiling order, a divine geometry that bound the cosmos together. In the years following his publication, Maxwell continued refining his theory, transforming it from abstract equations into a structured system. His treatise on electricity and magnetism, published in 1873, became a cornerstone of modern physics. The 2 volumes were dense and challenging, filled with both mathematical rigor and philosophical insight. They introduced the full set of equations that would later bear his name, unifying the concepts of electric and magnetic fields into a single framework. This monumental work not only summarized decades of research, but also opened doors to discoveries that Maxwell himself could only imagine. The world slowly began to catch up with his vision. Young physicists inspired by his writings began to test the implications of his theory. Among them was Heinrich Hertz, who in 1887, 8 years after Maxwell's death, confirmed experimentally that electromagnetic waves could indeed travel through space. Hertz's spark gap transmitter and receiver produced and detected waves just as Maxwell had predicted, proving that light, radio, and electricity were all part of the same continuum. This moment, often regarded as the birth of modern communication, was also Maxwell's vindication. His abstract mathematics had become physical reality, echoing across laboratories and eventually across the globe. Yet Maxwell's genius lay not only in what he discovered, but in how he thought. His vision extended beyond the boundaries of traditional physics. He saw fields as the true substance of the universe, more fundamental than particles or matter. This concept would later inspire the great revolutions of the 20th century. Einstein's theory of relativity, which showed that electric and magnetic fields merge into one entity under motion, and quantum field theory, which treats particles as excitations in underlying fields. Every modern theory of the cosmos, from the behavior of atoms to the structure of space-time, carries within it Maxwell's legacy. But during his own lifetime, Maxwell remained a modest man, far from the image of a triumphant genius. He was content in his quiet home at Glenlair, performing experiments in his workshop, surrounded by his wife Catherine, who was his constant supporter and companion. They shared a deep bond, built on intellect and affection. She helped him with his calculations, assisted in experiments, and often transcribed his notes. Together, they lived a life of simplicity, where science was not a career but a calling. Maxwell's approach to discovery was profoundly human. He believed that science should not merely describe the world but reveal its unity. In letters to friends, he often spoke of the joy of seeing patterns emerge from apparent disorder. Every discovery, he once wrote, is a harmony restored. That harmony, the unseen rhythm linking electricity, magnetism, and light, became the anthem of his life's work. Even as he delved into complex mathematics, he never lost sight of the beauty behind the numbers. His mind was both analytical and poetic, capable of turning equations into expressions of wonder. By the early 1870s, Maxwell knew that his theory would outlive him. He had built not just a model of nature, but a framework for future generations to expand upon. He saw science as a continuous dialogue, each discovery a note in an endless symphony. When he looked at his equations, he saw not only physics but philosophy, a glimpse into the unity that pervades all things. He once told a colleague, "The true aim of science is to find the simplicity which lies behind the apparent complexity of the world." His electromagnetic theory embodied that aim perfectly. Maxwell's equations would go on to reshape not only physics but technology, communication, and even human imagination. They became the foundation for radio, television, radar, and the digital networks that now connect humanity across oceans and planets. The invisible waves he predicted fill the air around us, carrying voices, images, and data through space, an everyday miracle born from his vision of unity. When we hold a phone, watch a broadcast, or observe the stars through a telescope, we are, in essence, touching Maxwell's invisible field, the same energy that lights the sun and flows through every atom in existence. His discovery of the electromagnetic field was not just a scientific milestone, it was a redefinition of reality itself. It revealed that the universe is not made of isolated fragments, but woven from continuous relationships. Every force, every vibration, every interaction is part of the same grand design. To Maxwell, that design was both beautiful and humbling. He had unveiled a truth that transcended his time, a truth that light, electricity, and magnetism are not separate forces but one universal phenomenon, the pulse of the cosmos. James Clerk Maxwell's journey from conceptual insight to mathematical perfection, marked the birth of a new scientific language, one that could speak to the invisible. The second half of this story is a deep look into how he translated ideas into precise formulations that would forever reshape the study of energy and fields. Maxwell didn't just stumble upon these equations, he built them piece by piece, driven by a lifelong fascination with unity and simplicity in nature. To him, equations were not mere symbols but reflections of truth, a poetic representation of how the cosmos communicates. His understanding of mathematics was profound, but what made him extraordinary was his ability to see physical beauty through mathematical form. While others saw numbers, Maxwell saw relationships, waves that intertwined, fields that breathed, and forces that danced in synchrony. In the mid-1850s, scientists like Michael Faraday had already observed electromagnetic phenomena, but Faraday's ideas were expressed through visual field lines and experimental intuition rather than mathematics. Maxwell revered Faraday and wanted to give his ideas a precise mathematical body. He began developing a set of equations that could express the behavior of electric and magnetic fields. This was not an easy task. It required uniting abstract mathematics with the tangible results of experiment, two worlds that often resisted one another. Yet Maxwell's genius lay in his capacity to bridge them. In 1861, his paper, On Physical Lines of Force, became the foundation of a revolutionary framework. He introduced the idea that fields themselves were real entities, not just convenient tools for calculation. The world of invisible electric and magnetic influence became, through his eyes, a living continuum that filled space. The more Maxwell refined his ideas, the more he realized that these forces could not exist independently. He saw that electric and magnetic fields are intertwined. Changes in one create changes in the other. Through intense work and deep contemplation, he derived the now famous set of equations that describe this relationship. These equations explain that an oscillating electric field produces a magnetic field, and vice versa, leading to self-propagating waves, electromagnetic waves that travel through space at a finite speed. When Maxwell calculated that speed, he found it matched the measured speed of light. This was the moment of revelation. Light, the mysterious and ancient phenomenon that had puzzled philosophers and scientists for centuries, was nothing but an electromagnetic wave. In one sweep of insight, Maxwell had united light, electricity, and magnetism into a single theory of the electromagnetic field. This unification was not just a scientific achievement, it was a philosophical one. It changed how humanity perceived reality itself. Before Maxwell, forces were thought to act instantly at a distance, as if one object could affect another across empty space without mediation. Maxwell replaced this notion with a field that fills all of space, a medium through which forces travel in continuous motion. The universe, in his view, was no longer composed of isolated particles, but of dynamic fields woven together in an intricate, ever-changing tapestry. This idea became the foundation upon which Einstein, Planck, and others would later build. The concept of the electromagnetic field was so powerful that it redefined not only physics, but also our understanding of causality and space-time. Maxwell's work demanded an extraordinary balance of imagination and discipline. He could visualize forces as geometric structures and express them with elegant equations. His notebooks reveal a mind both poetic and precise, blending physical intuition with mathematical artistry. In a time before computers or advanced instruments, every calculation had to be done by hand, every hypothesis tested through pure reasoning. Yet Maxwell thrived in this intellectual solitude. His letters show that he often discussed these concepts with humor and humility, never losing his childlike wonder at nature's hidden mechanisms. He referred to his field theories as mental experiments, and he took joy in the act of discovery as much as in the result. When Maxwell published his treatise on electricity and magnetism in 1873, the world was not immediately ready to appreciate its depth. Many scientists of his day found the mathematics too abstract, the physical interpretation too unfamiliar. Yet over time, as others verified his predictions and explored his implications, his ideas began to take root. Heinrich Hertz's experiments in the 1880s would later confirm the existence of electromagnetic waves, proving that Maxwell's vision was correct. These discoveries set the stage for the development of radio, radar, and eventually modern communication technology. What began as mathematical equations on paper became the foundation of the technological world that surrounds us today. In reflecting on Maxwell's genius, one cannot separate the beauty of his mathematics from the curiosity that drove him. He believed that the universe was intelligible, that every mystery could be expressed in the language of logic and symmetry. His equations were not cold abstractions, but living expressions of unity. To him, science was not merely about prediction or control, it was about understanding the harmony of existence. Each symbol carried meaning beyond its form, and every formula was a glimpse into nature's soul. It is this harmony that made Maxwell's work timeless. Long after his passing, physicists still refer to his equations as one of the greatest syntheses in the history of thought, a unification not just of forces, but of human intellect and the cosmos. As we look back, the magnitude of Maxwell's achievement continues to expand. His unification of electricity, magnetism, and light was a turning point that revealed the deep connection between energy and space. It became the cornerstone upon which quantum theory and relativity would rise. Einstein once said that the work of Maxwell was the most profound and fruitful that physics had seen since Newton. Indeed, Maxwell did for fields what Newton had done for motion. He gave them laws that governed the universe. But while Newton's world was one of masses and forces, Maxwell's was one of vibrations and waves, an invisible ocean of energy pulsing through all of creation. His vision anticipated the invisible networks of the modern age, from wireless communication to cosmic radiation, proving that the universe itself is a grand electromagnetic symphony. In his later years, Maxwell's attention turned to refining his theories and sharing them with a new generation of scientists. Despite his failing health, he continued to teach, write, and explore new questions. He understood that his equations were only the beginning, that the field concept would lead to new revolutions yet to come. In this way, his work embodied the essence of scientific progress, the belief that truth is not static but ever evolving. He once wrote, "The aim of science is to find unity in diversity." These words capture not just his philosophy, but the spirit of all scientific inquiry. Maxwell's unification of electromagnetic forces became the first great step toward understanding the interconnectedness of all physical phenomena. Even today, Maxwell's equations remain a cornerstone of modern physics. They describe not only the behavior of electric and magnetic fields, but also underpin the operation of everything from power generation to satellite communication. Each technological advancement that transmits, receives, or manipulates electromagnetic energy owes its existence to Maxwell's insight. Yet beyond their utility, these equations represent something more profound: the idea that nature operates through elegant simplicity. What seems complex on the surface is, at its heart, governed by deep and beautiful order. This realization is perhaps Maxwell's greatest legacy, the knowledge that understanding the universe is within human reach, and that mathematics is the key that unlocks its most secret chambers. James Clerk Maxwell's journey toward the formulation of his equations is a testament to the power of imagination fused with reason. His ability to perceive the unity behind diverse phenomena transformed science from a collection of observations into a coherent description of nature's design. Through his genius, humanity gained not only a new understanding of light and electromagnetism, but also a new way to think about the world, one that celebrates the harmony between mathematics, physics, and the very fabric of reality. Maxwell's work endures not because it solved every mystery, but because it revealed that behind every mystery lies a pattern waiting to be found. His life's mission, to uncover the hidden symphony of the universe, remains a beacon for all who seek truth in the dance of the unseen. When James Clerk Maxwell unveiled the deep connection between electricity, magnetism, and light, he accomplished something no scientist before him had dared to dream. He unified the great forces that power the universe. The fourth keynote in his legacy represents this extraordinary realization, the unification of electricity, magnetism, and light into a single coherent framework. It was a moment in history when the boundaries between phenomena blurred, and nature revealed one of its most elegant secrets. In the mid-19th century, scientists understood electricity and magnetism as separate entities. They knew that electric currents could produce magnetic effects and that magnets could influence electric materials, but no one truly grasped why these forces behaved this way or whether they were connected at all. Light, on the other hand, was a complete mystery. It was studied by physicists and philosophers alike, but no one could definitively say what it was made of or how it traveled through space. Some thought of it as a stream of particles, others as a wave in a mysterious substance called the ether. Maxwell was determined to find the truth. By carefully studying the experiments of pioneers like Faraday, Maxwell recognized patterns that others had missed. Faraday had visualized magnetic fields as lines of force, invisible structures that filled space around magnets and electric currents. Most scientists regarded this idea as a visual aid, not a literal description of nature. But Maxwell saw it differently. He believed that these lines of force were real, that the field itself was an essential part of reality. Through years of deep analysis, he began to express Faraday's observations in the precise language of mathematics. This was the birth of a new scientific language field theory. In this framework, Maxwell discovered that a changing electric field creates a magnetic field, and a changing magnetic field, in turn, generates an electric field. When these two interact, they form a self-sustaining wave that can travel through space without any physical medium. This was the most astonishing insight of his career. The realization that light itself is an electromagnetic wave. When Maxwell calculated the speed of these waves, he found something breathtaking. The result matched the known speed of light. It was no coincidence. This was a revelation that forever changed the human understanding of reality. Light is electricity and magnetism in motion. The glow of a candle, the colors of the rainbow, the starlight that travels millions of years across space, all are manifestations of electromagnetic energy. In one stroke of genius, Maxwell united three previously separate domains of physics into one. This was more than a discovery. It was a unification of nature's forces at the deepest level ever achieved at the time. Maxwell's equations became the bridge between the seen and the unseen, transforming light from a mystery into a consequence of fundamental physical laws. The consequences of this unification were immense. Maxwell's theory didn't just explain light, it predicted the existence of many other types of electromagnetic waves that no one had yet detected. These included radio waves, microwaves, infrared radiation, ultraviolet light, X-rays, and gamma rays. Within a few decades, Heinrich Hertz experimentally confirmed the existence of electromagnetic waves, proving that Maxwell's vision was right. This single discovery laid the foundation for the technological world we live in today. From radio and television to Wi-Fi, radar, and even satellite communication, every device that uses wireless energy owes its existence to Maxwell's unified theory of electromagnetism. But beyond technology, Maxwell's unification carried profound philosophical meaning. It showed that the universe is not a collection of separate phenomena, but an interconnected system governed by universal laws. What we perceive as different forms of energy, light, heat, magnetism, and electricity, are all part of one grand continuum. This realization inspired future generations of physicists to search for even deeper unifications. Albert Einstein, deeply influenced by Maxwell's work, later extended these ideas into his theory of relativity. In many ways, Maxwell paved the way for the modern quest to unify all fundamental forces. The dream of a theory of everything. Maxwell's unification of electricity, magnetism, and light stands as one of the greatest intellectual achievements in history. It represents the moment when humanity began to truly see the invisible structure of the cosmos. His equations captured the harmony of nature in mathematical form, 4 elegant lines that describe how energy moves and interacts across the universe. Today, scientists and engineers use these equations to explore everything from the smallest electronic circuits to the vastness of interstellar space. They are a constant reminder that the universe operates under principles of simplicity and unity, principles that Maxwell uncovered through pure thought and imagination. His discovery was not just about physics, it was about perspective. It transformed how humans understand the fabric of existence. It revealed that light, the very essence of sight and life, is woven from the same forces that flow through a simple wire or spark in a stormy sky. Through this realization, Maxwell showed that nature speaks a single language, and those who learn to read it can see the hidden symmetry that binds all things. The unification of electricity, magnetism, and light remains not only a triumph of science, but also a symbol of human curiosity, the power of the mind to connect the dots between the visible and the invisible, and to discover the underlying beauty of the universe itself. The impact of James Clerk Maxwell's discoveries on modern physics is so vast that it is difficult to find a single area of science untouched by his genius. His work became the foundation upon which the 20th century's greatest scientific revolutions were built. Before Maxwell, physics was largely the study of matter in motion, the mechanics of how objects moved and interacted through forces like gravity. But after Maxwell, physics became the study of fields, waves, and energy. His equations redefined not only electricity and magnetism, but also the very concept of how information and influence travel through space. He turned invisible forces into quantifiable laws, revealing that the universe is not empty but filled with a dynamic, vibrating field that connects everything. This understanding shifted humanity's view of reality from a mechanical universe to one that was living and interconnected, pulsating with waves of energy and light. One of the greatest impacts of Maxwell's work was its direct influence on Albert Einstein and the development of the theory of relativity. Einstein once said that the work of Maxwell was the most profound and fruitful that physics has experienced since the time of Newton. Maxwell's equations showed that light always travels at the same speed in a vacuum, no matter how fast the observer moves. This simple but powerful truth inspired Einstein to question the nature of space and time itself. Without Maxwell, there would have been no special relativity, no understanding that time slows down and lengths contract when objects move close to the speed of light. Maxwell's constant, the speed of light, became the cosmic speed limit and the cornerstone of modern physics. It was this insight that helped Einstein realize that energy and mass are two sides of the same coin, expressed in his famous equation E=mc². Thus, Maxwell's work did not just unify electricity, magnetism, and light, it laid the groundwork for the unification of space, time, and energy. Beyond relativity, Maxwell's equations also prepared the stage for quantum physics, another pillar of modern science. The study of light as an electromagnetic wave eventually led scientists like Max Planck and Niels Bohr to explore how light interacts with matter on the smallest scales. Their discoveries gave birth to quantum mechanics, a field that governs atoms, particles, and energy at the microscopic level. The photon, the particle of light, is both a wave and a particle, a duality that stems directly from the wave, like nature of light that Maxwell first revealed. In this way, Maxwell's legacy extends into every corner of modern physics, from the structure of atoms to the behavior of the cosmos itself. Every step in humanity's journey toward understanding the universe, relativity, quantum theory, particle physics, and cosmology, begins with the field equations that Maxwell crafted in the 19th century. The technological impact of Maxwell's discoveries is equally profound. His equations predicted that electromagnetic waves could exist beyond visible light, and this prediction gave rise to radio, radar, television, and eventually wireless communication. When Heinrich Hertz experimentally confirmed the existence of these waves, it was the beginning of a technological revolution that continues today. Every mobile phone, every satellite transmission, every Wi-Fi signal, every X-ray and MRI scan operates on principles that Maxwell discovered. His ideas not only explained nature, but also allowed humanity to harness it. The modern world, interconnected through invisible signals and energy, is a living testament to his genius. It is not an exaggeration to say that Maxwell's work powered the technological age, shaping the way humans communicate, explore, and understand their environment. But perhaps the greatest impact of Maxwell's discoveries lies not only in the equations themselves, but in how they changed the philosophy of science. Before Maxwell, the universe was seen as a collection of separate forces and phenomena, each governed by its own laws. After Maxwell, scientists began to search for unity, to look for deeper connections between seemingly different aspects of nature. His success in uniting electricity, magnetism, and light inspired future generations to seek even greater unifications, leading to the development of unified field theories and the modern standard model of particle physics. In essence, Maxwell taught science how to think differently, to look for simplicity within complexity, to believe that all of nature is woven from the same underlying fabric. Even today, Maxwell's influence continues to expand. His equations are not relics of history but living tools, still used to explore new frontiers of physics. They are used to design spacecraft, understand plasma in stars, simulate electromagnetic fields in computers, and study the behavior of black holes. His vision anticipated technologies that didn't yet exist in his lifetime: fiber optics, lasers, and even quantum communication. The power of Maxwell's thought lies in its timelessness. His work continues to guide human understanding more than a century after his death, proving that true genius transcends its era. Maxwell's legacy reminds us that science is not only about answering questions, but about revealing deeper layers of harmony within the universe. He gave humanity a way to see the invisible, to understand that everything, from the light of the sun to the electricity flowing in a wire, is part of the same grand symphony of energy. His discoveries bridged the gap between the known and the unknown, showing that the natural world operates under principles of balance and unity. In the vast network of modern physics, from relativity to quantum theory, his fingerprints are everywhere. Every photon of light, every magnetic pulse, every radio wave that travels through the air carries a trace of Maxwell's insight. His equations are not just mathematical symbols, they are the heartbeat of modern science, echoing through every discovery that has followed. Through his work, Maxwell transformed the human understanding of the universe, not just by describing its laws, but by revealing its profound and unbreakable unity. James Clerk Maxwell's influence on the generations of scientists who followed him was profound, shaping the very direction of modern physics and inspiring minds that would change the world. His work did not end with his own discoveries; rather, it became the foundation upon which countless others built new theories, technologies, and philosophies of science. Maxwell's equations, those elegant expressions of the relationship between electricity, magnetism, and light, became a universal language for understanding the unseen forces of nature. When later scientists encountered the beauty and power of these equations, they were not merely reading mathematics, they were gazing into the structure of reality itself. Maxwell's genius sparked a revolution that rippled across decades, influencing figures like Albert Einstein, Niels Bohr, Erwin Schrödinger, and many others who would expand his vision into the modern scientific age. Albert Einstein was perhaps the most direct and vocal heir to Maxwell's legacy. Einstein often spoke of how deeply he admired Maxwell's work, calling it the most profound and fruitful that physics has experienced since Newton. It was Maxwell's realization that the speed of light is constant that pushed Einstein to reconsider the nature of time and space. Before Einstein, scientists assumed that time and distance were fixed. absolute quantities that never changed. But Maxwell's equations hinted otherwise. They showed that the speed of light remained the same for all observers, no matter how fast they were moving. To make sense of this, Einstein developed his theory of special relativity, which fundamentally altered human understanding of space, time, and energy. In this way, Maxwell's insight into electromagnetic waves directly led to one of the greatest breakthroughs in history. A theory that would explain everything from atomic reactions to the bending of light near massive stars. Maxwell's ideas also deeply influenced the birth of quantum mechanics, which governs the strange and unpredictable behavior of matter and energy at the smallest scales. His concept of light as a wave was later expanded by Max Planck and Albert Einstein, who discovered that light could also behave like a particle, the photon. This duality, wave and particle existing as one, emerged from Maxwell's revelation that light is electromagnetic in nature. Without Maxwell, the quantum revolution might never have begun. Scientists like Niels Bohr and Schrödinger, who explored the structure of atoms and the mysteries of energy levels, carried Maxwell's spirit forward, combining mathematics and imagination to probe deeper into nature's design. His influence was like a guiding thread running through every major discovery of the 20th century, linking the old world of classical physics with the new world of quantum and relativistic science. Beyond theory, Maxwell's work inspired technological revolutions that reshaped civilization. His prediction that electromagnetic waves could travel through space led directly to the development of radio and wireless communication. When Heinrich Hertz confirmed these waves experimentally, he opened the door to inventions that changed the way humanity connects. The telegraph, radio, television, radar, and eventually the internet. Every signal transmitted without wires, every image broadcast across the globe, is a living extension of Maxwell's equations. The scientists and engineers who built these technologies all worked under the shadow of his ideas. Even in space exploration, Maxwell's influence continues. His theories describe how radiation travels through the vacuum of space, guiding the communication between Earth and distant spacecraft. In every sense, Maxwell became the silent architect of the modern technological age. But Maxwell's impact went deeper than technology and mathematics. It touched the philosophy of science itself. He showed that the universe could be understood not through isolated observations, but through unified principles, that everything is connected by underlying laws that express harmony rather than chaos. This philosophy inspired countless scientists to search for unity in diversity, to look for common threads between different forces of nature. The great unification projects of the 20th and 21st centuries, the search to link electromagnetism, gravity, and the nuclear forces, are all driven by the same belief that guided Maxwell. His success proved that unity is not a dream but a reality waiting to be uncovered. It changed how humanity viewed the cosmos, no longer as a machine of separate parts, but as a seamless web of energy and interaction. Maxwell's influence also extended to education and scientific thought. He established rigorous methods of experimentation and mathematical analysis that became the model for modern physics. His treatise on electricity and magnetism was not just a scientific text, it was a declaration of a new way of thinking. Generations of physicists learned from it, building on its principles to explore new frontiers. It became the bridge between classical science and the modern theories that define our age. Through his writing, Maxwell taught scientists to think in terms of fields rather than particles, to view forces not as distant interactions, but as local phenomena spreading through space. This shift in perspective continues to shape scientific research even today, from cosmology to quantum field theory. Einstein once reflected that Maxwell's equations were the foundation upon which all modern physics stands, and that no theory since had displaced them, only expanded upon them. This statement remains true more than a century later. Maxwell's influence lives on in every new discovery, every technological leap, and every scientific idea that seeks to understand the universe more deeply. His legacy is woven into the very fabric of science, a testament to how one mind's vision can illuminate the path for generations. Even now, as physicists strive to unify all the fundamental forces in a single theory of everything, they walk the path Maxwell first opened, the belief that nature is governed by harmony, not division. In the end, Maxwell's greatest influence may not be found in equations or inventions, but in inspiration itself. He proved that human curiosity, guided by imagination and reason, could uncover the deepest truths of existence. His work showed that science is not only about solving problems, but about revealing beauty. The beauty of order, symmetry, and unity. The scientists who followed him, from Einstein to the quantum pioneers, inherited not just his discoveries, but his way of seeing the world as a place where every mystery hides a connection, and every force is part of one grand design. James Clerk Maxwell's influence on future generations is immeasurable, not because of how much he changed science, but because he changed the way humanity thinks about the universe, as an elegant, interconnected masterpiece waiting to be understood. The legacy of James Clerk Maxwell stands as one of the most enduring and transformative in the history of science, a legacy that transcends his lifetime and continues to shape how humanity understands the universe. Maxwell's work did not merely solve problems or describe natural phenomena, it redefined what science could be. His vision revealed that beneath the complexity of nature lies a profound unity, a mathematical harmony that connects all things. More than a century after his death, his name still echoes through every laboratory, every communication system, and every scientific theory that seeks to explain the cosmos. Maxwell's legacy is not confined to his equations alone. It lives in the very philosophy of science, the pursuit of truth through beauty, logic, and imagination. Maxwell's timeless influence begins with the idea of unification. Before him, electricity, magnetism, and light were seen as separate phenomena, each governed by its own laws. He changed that forever by revealing they were aspects of one single force, the electromagnetic field. This revelation was not just a scientific discovery, it was a philosophical awakening. It taught the world that the universe is not fragmented, but woven together by invisible threads of energy. This concept became a guiding light for every major scientific revolution that followed. Einstein's relativity, Planck's quantum theory, and the modern search for a theory of everything all trace their intellectual roots back to Maxwell's unifying vision. His work demonstrated that understanding the universe means seeking the connections that tie its forces together, and this belief continues to drive scientific inquiry today. But Maxwell's legacy extends beyond physics into the very way we live. Every modern technology that uses electromagnetic energy, from radio and television to Wi-Fi, X-rays, and GPS, owes its existence to the principles he discovered. When you speak on a mobile phone, watch a broadcast, or send a message across the world, you are witnessing Maxwell's vision in motion. The invisible waves carrying those signals are his legacy in action. His equations, once confined to the chalkboards of the 19th century, have become the backbone of the digital age. They connect continents, guide spacecraft, power cities, and enable the exploration of distant galaxies. It is remarkable to think that one man's equations, written in the quiet of his study, could give rise to the interconnected world humanity now inhabits. Maxwell's impact also lives in the hearts of scientists who followed his path. He proved that science is not only about experimentation, but also about imagination. His ability to see unity where others saw separation inspired generations of thinkers to look deeper into nature's mysteries. Maxwell's legacy is the belief that knowledge is not static but ever expanding, that each discovery opens new doors of understanding. He taught that true genius lies not in knowing everything, but in asking the right questions. Einstein once said that his own theory of relativity would never have been possible without Maxwell's shoulders to stand on. Similarly, modern physicists who study quantum fields, black holes, or cosmic radiation continue to build upon the foundation Maxwell laid. His vision of an interconnected universe remains a guiding principle for every scientific frontier. Yet Maxwell's legacy is not only scientific, it is human. He embodied the spirit of curiosity, humility, and wonder that defines the pursuit of knowledge. Despite his genius, Maxwell was known for his kindness and modesty, often describing his own work as part of a larger quest to uncover nature's beauty. He saw science as a form of art, an exploration of patterns, symmetries, and relationships that mirror the harmony of the natural world. In an era when technology and discovery were rapidly advancing, Maxwell reminded the world that science was not about domination, but about understanding, about seeing the unity of all things. His words and writings reflect a mind deeply attuned to both logic and poetry, blending rigorous analysis with a profound sense of awe for the universe's mysteries. As time passed, Maxwell's work proved to be far ahead of its era. Many of his predictions were confirmed only decades later, when technology finally caught up with his imagination. This lasting relevance speaks to the depth of his insight. His theories did not fade with the passing of time. Instead, they grew more significant as science evolved. Every new discovery, from the quantum field to the electromagnetic spectrum, only confirmed his vision of a connected universe. Maxwell's equations have stood unchallenged for more than 150 years, a testament to their perfection. They are as valid today as the day he wrote them, a rare and powerful example of eternal truth in human knowledge. In education, Maxwell's influence endures as well. His approach to learning and discovery continues to inspire teachers and students around the world. His work encourages curiosity, patience, and a belief in the power of ideas. He showed that the path to understanding is not always linear. It requires imagination, persistence, and faith in the unseen. The next generation of scientists, those exploring quantum computing, renewable energy, and interstellar travel, are all walking the trail Maxwell first illuminated. His life and work remain proof that science is a journey of discovery that never ends, a dialogue between the human mind and the vastness of the cosmos. Ultimately, Maxwell's legacy is the realization that the universe is a unified whole, a grand interplay of forces, patterns, and light. He taught humanity to see beyond the visible, to recognize that the same laws that govern a flicker of light in a lamp also shape the glow of distant stars. His vision connected the smallest spark to the greatest galaxy, showing that all of existence is bound together by the same fundamental principles. This understanding forever changed how humans perceive their place in the cosmos. Through his equations, Maxwell gave us more than scientific knowledge. He gave us a new way to see reality, as a living, breathing symphony of energy and harmony. James Clerk Maxwell's legacy is, in essence, the story of how one mind transformed the world's understanding of the universe. His work bridged the gap between the seen and the unseen, between mystery and explanation. It continues to inspire the pursuit of knowledge, the creation of technology, and the endless human quest to uncover the truth. His equations remain timeless, his vision boundless, and his influence eternal, a reminder that even one person, guided by curiosity and imagination, can unveil the invisible forces that shape the universe and, in doing so, illuminate the path for all who follow.